Hello, I'm Bill Steele, a faculty member here at York College of Pennsylvania, part of the chemistry program, and this is YCP Chemistry Labs. If you're a returning student to York College, you're familiar with our YouTube channel that's designed to help you get ready for lab each and every week. If you're new to York College this semester, let me welcome you. Each week we'll have a video that prepares you for lab. I'll be here to overview the concepts being covered in the lab experiment, discuss any safety considerations, and go over the pre-lab questions, all in an attempt to have you as ready as possible for lab when you arrive for your assigned time, and then hopefully get out of lab as quickly as possible. So this week we're talking about our first experiment of the semester. We're going to cover safety information in lab, as it's also the first meeting of the semester, but the experiment that we'll be doing this week is the calorimetry experiments. That's where we start our study of topics in the lecture part of the course, and hopefully by now you've heard at least a few of these terms that you'll hear me use during the pre-lab lecture today. So our goal in the lab today is to conduct a series of reactions, 4 different reactions involving 4 different but yet somewhat related chemicals, all reacting with acid, in an effort to see which reaction produces the greatest amount of energy. All right? We're going to use different masses, which is a little bit of a trick in this whole consideration, or a little bit of a decoy, because using more mass might not necessarily mean more energy per number of particles, right? So per mole is how we're going to be quantifying that energy. So let's look at some of the concepts that'll be in play. Anytime we have a reaction conducted, it's surrounded by literally the rest of the universe, or the surroundings. In lab today, we're going to use a calorimeter so that our reactions don't just give off energy to the entirety of the universe, but rather to a well-defined amount of volume and of material that we know and study very carefully. And so in our calorimeter, the surroundings, we're actually going to have a little glass cup or beaker inside our calorimeter filled with a certain amount of liquid. That liquid is the surroundings of our chemical reaction. Keep that in mind today. Right? And we can easily measure the temperature of that liquid. And as its temperature changes, the amount of energy present in the liquid is being changed. And all of that energy coming into our liquid has come from our chemical reaction. So it's an equal amount of energy. The only difference is who has the positive sign and who has the negative sign. All right. The surroundings, we're going to see their temperature increases, which means their energy is increasing. And in thermodynamics, we use a positive sign to represent that type of change, increase in energy. Therefore, the chemical reaction that's experiencing in the same system here is giving off or releasing energy, losing energy to its surroundings, we might say. That would be associated with a negative sign. And so while the number would be the same, let's say 125 kilojoules on each side, for example, for the reaction it would be negative 125 kilojoules, for the surroundings positive 125 kilojoules. Okay? Now how are we going to know how much energy our surroundings absorbed? All right? We use 2 different formulas for the calculation of energy transfer, or heat flow. Q is this symbol for heat, or what we often commonly say as heat flow. When there is a temperature change for the thing that you're studying, in this case the surroundings, this liquid here, we use the formula that the heat is equal to the mass of the system under study times its specific heat capacity, a constant unique to each and every type of material that we might use in an experiment, and then the change in temperature of the system. So this will be pretty straightforward. You will know the mass of your system, because you will have measured by either volume and or mass what you put into the calorimeter. It will be the entire system. Once you add the other reactant to start the reaction, it appears to have disappeared, right, to the naked eye, but its mass is still in there. So if we had 100 grams of liquid but added 5 grams of solid into that, which dissolved, the total mass would be 105 grams that we would use in this experiment. All right? And then we'll use a thermometer to measure the change in temperature. Pretty straightforward. So that will tell us the total amount of energy gained by our surroundings and thus released by our chemical reaction. All right? Now, when we want to quantify how much energy is released by the reaction per mole, we need to use a different formula. The reaction is actually occurring at a constant temperature, and it's the surroundings that experienced the constant temperature. So if we took the heat from the surroundings to become the heat of the reaction, what's happening in terms of the reaction is the amount of heat, that same number, is related to how many moles, that's what this N represents here, how many moles of the limiting reactant reacted, multiplied by a constant which is called the enthalpy of reaction. This is really the unit cost of this chemical reaction. How much energy it releases or potentially absorbs, although today's reactions are exothermic, so they're releasing. So it's how much energy it releases per mole of the reactant that's used. It's a lot like, as I said, a unit price, like at the grocery store. Apples are maybe $2.50 per pound. So a chemical reaction might release 180 kilojoules per mole of the chemical reactant. So if we consider this equation here for the reaction, we will know the energy, the heat that was released by the reaction. We're getting that from the calorimeter by studying the surroundings. The surroundings told us how much heat the reaction released. So then we'll know this, and we will also have measured the amount of our limiting reactant. Therefore, we're going to manipulate this equation to solve for this unit energy per mole. Q divided by N will be the enthalpy change of each of the respective reactions. And once we've done this, we have a similar sort of comparative unit. Heat per mole, joules per mole, or kilojoules per mole. And so you could study the 4 different chemical reactions making equally, I should say, once you put your data into this format here. And so the reactions today all involve hydrochloric acid with a different solid. The 4 solids are going to be magnesium, magnesium oxide, zinc, and zinc oxide. So 2 pure metals, magnesium and zinc, and then 2 oxides of those metals. And in this group of 4, when we're all done, we'd like to compare how much energy is being released per mole of the solid. So the solid is going to be set up in all of our cases to be that limiting reactant that you'll use in this equation here as part of your calculations after lab today. Okay. As far as safety considerations go today, just a couple of things to point out. The acid that we're working with is sort of intermediary in its concentration, so do please be careful. Don't splash a lot of it around. If you get any on your skin, please go to the sink and wash it off as quickly as possible. All the reactions are exothermic, and they are releasing heat, so keep that in mind. You will see some steam and bubbles during the reaction, but that's not going to be any safety hazard. And 2 of the reactions will also produce hydrogen gas. The 2 metals produce hydrogen gas when they react with the acid, and so that hydrogen gas will be vented. We want to make sure that we absolutely have no sources of flame in the lab today, since that hydrogen is flammable. But there's no use of Bunsen burners anywhere else in the lab today, so that should not be a real problem that we have to worry about. Okay? As far as other considerations for the lab, you're going to set up your calorimeter by removing the little metal cup that actually comes into calorimeter and inserting a glass or Pyrex beaker into it. The metal would be corroded by the acid that we're using in the lab. So make sure, that's one of the first steps in the procedure, make sure you use the glass beaker on the inside of your calorimeter. Okay? You will put this on top of a stir bar, plate to help stir and promote that chemical reaction as well. That's another slight consideration. Please make sure you only use the stir feature, not the heat feature. You would not want to be adding energy, heat, to this system from outside. The idea of the calorimeter is all of the energy in here stays in here from the chemicals that are present. Okay? We don't want anything from the outside coming in. Okay? All right. Let's look at the pre-lab questions real briefly and give you a little bit of a hint on how to solve each of them. The first two have really direct relationships to calculations that you'll do as part of the lab work. So they're great practice. In the first question, we're looking at a sample of water that undergoes a temperature change of 7.25 degrees Celsius. And we're asked about how much heat must be absorbed by the water. So we've already seen the formula that we're going to use. You would simply use the heat is equal to the mass of the water times the heat capacity of the water times the change in temperature that the water undergoes. So you'd multiply these three terms together to come up with the answer. In this case, the units would end up being in joules, but typically if you get an answer that is over 1,000 for heat, it would be common to convert that into kilojoules. So just keep that in mind when you do calculate your answer. You may or may not be at that point. Okay. In our second question, we're asked about what's called the enthalpy of solution. Similar to the enthalpy of a reaction here, but there's no actual reaction taking place when we dissolve the ammonium nitrate into some water. But there was a heat change experienced by the water. And that's due to the reaction, or not the reaction, sorry, the chemical absorbing or possibly releasing energy when the chemical dissolved. So here, for the dissolving process, which would be at a constant temperature, we would use Q equals N times delta H. And instead of delta H reaction, we'd call it the delta H solution down here. But this is the term that we're interested in, so we could solve this much like we'll be doing in the lab, although we'll do it for a reaction in the lab. We could solve this for the enthalpy of solution being the heat change experienced divided by the moles of the chemical. So what you have to do in this case first is convert mass to moles. And then second, you would use this equation to calculate the enthalpy of solution. The third question demonstrates how we calculate the heat change or the enthalpy change of reactions that we can't conduct in the laboratory for various reasons, either safety or lack of chemicals, but we can still figure out what their enthalpy change is. And it makes use of a very powerful tool called Hess's law. Hess's law of heat summation says if we have a reaction that we don't know its energy change, but yet we can express that reaction as somehow the sum or the combination of other reactions, we will be able to calculate the heat change, energy change of the reaction we're interested in from the energy changes of those known reactions. And so if we look at the reaction that I've written in blue down here, we don't know what its energy change is, but this reaction is related to these other two. But their pieces are like a puzzle. We have to kind of rotate them and put them in the right places. And so for example, N2O5 is here on the left side, the reactant side of this reaction, but I want it on the right side. So I could reverse that first reaction and write it instead as 2NO plus 3/2 O2 produces N2O5. When I do that, the energy is also reversed, negative of the 223.1. Because this reaction absorbs 7 kilojoules. So when we reverse it, the opposite direction the reaction would release. And so by multiplying by -1, we'll get that negative sign, that release of energy. Okay? And then, let's see. In my overall reaction, I need 2 NO2s. Okay? This second reaction has 1 NO2, and it happens to be on the wrong side again. So I'm going to reverse that reaction, NO2, producing NO plus 1/2 an O2, and I'm going to double it. So the energy, in effect, would be -2 times the -57.1 kilojoules. Because this reaction is happening twice, and this is the energy per one, so to speak, one time of this reaction. So if it's happening twice, there'll be twice as much energy involved. And again, we reversed it, so that changes the sign of the energy. When I add these together now, these two reactions, notice that I will end up with some cancellation. I have to do a little bit of distribution here, but I'll have, let's see, 2 NOs canceling with those 2 NOs. And I'll have an entire 1 unit of O2, which will cancel out some of the O2 here, leaving me with 1/2. So my net reaction is going to be 2 NO2s plus 1/2 of an O2. These things were left over. And on the right side, I've produced my N2O5. So you can see I've been able to express this target reaction as the combination somehow of these other two reactions. Which means that the energy change then of my reaction is simply going to be this sum right here. So you would now just need to take into account the signs and the coefficient that you've added, and then combine those numbers, and that would be the enthalpy change of this new reaction. So there's your pre-lab questions, and you should be all set to fill those out and hand in your pre-lab page as you get started. Okay? So that's about it for today. One other thing to tell you a little bit about this procedure is, while there are 4 different reactions to be done, you'll only be conducting 2 of them in the lab and then sharing your data with your classmates. It's a little more efficient way for you to study all these reactions, and then you can do a single reaction or your 2 reactions multiple times to ensure hopefully some consistency in your results. So that's one other thing that you'll see in the procedures. With that, I'll wish you a good day in the lab and a good start to the semester. Take care.